Hey, Honors Calc, Mr. Tan here, reporting from 502. Hope everybody's doing okay on this Wednesday. So what I wanted to go over was two more examples from going over these definite integrals that require u-substitution. And this example, actually, when I was first working through it, had me stumped for a bit. It's sort of like that other one that I had made the video of. But then what I realized was what I was able to do was look at this list of definite integrals. And you can see I'm already scrolled down here because this one fits this format, the 1 over x squared plus 1, which has a perfect integral, which is arctan of x. And so I was thinking, well, is there a way I could, if this is 1 over x squared plus 1, well, if I could think of this as a u squared, that would make it quite easy for me to integrate. So I thought, well, what's the square root of 3x squared? And I thought, well, if I took the square root of 3x squared, it would just be root 3 times x outside of the square root. And the reason I'm choosing to do so is because I know that then it would be a nice integral for me to tackle. So if that is my u value, my du is just going to be quite simply root 3 dx. And now, what I've sort of, since our last lesson, what I've been seeing is, yes, we could leave it in terms of these x values, substitute it, and then evaluate. But it seems like the more accepted method, and you can obviously pick and choose when it makes more sense, but if u equals, and let me erase this in between steps so I don't get confused moving forward. If u equals root 3x, well, what I could do if I want to plug these in for x, I could rewrite this whole integral in terms of u. So let's take a look at how that would look. Well, if I rewrite this as root 3, if I plug in 1, I just get root 3. If I plug in negative 1, I just get negative root 3. Oh, well, I could do the method where I think about, let me solve for dx to plug that in. So if I divide du by root 3, I would get dx. Now I can substitute right in because this is just going to be u squared, and the dx now we have it in terms of du. Maybe it would be better for me to write as 1 over root 3 du. So let's take a look-see. So this becomes 1 over 1 plus, well, this is just u squared. That's what I actually did to find what u is. And then dx, I'm replacing it with 1 over root 3 times du. Hey, Miss Stanford, how are you? Want to hop in my video for my Honors Calc students?
Ooh, Honors Calc. Hi.
So now that I've got 1 over root 3, well, that's a constant, so that can come out in front of my integral. And then I just have this 1 plus u squared du. And although this is written backwards, it's still, the integral of that is one of my known trigonometric integrals, which is just the arctan of u. And then I need to evaluate that at root 3, from negative root 3 to positive root 3. So when I go about doing this, let me zoom out a little bit so you can see from wherest we came. Is that a word? Nobody knows, I guess. Alright, so I would just end up, as you start seeing like that factor, I guess I should have been doing parentheses all the way, or sorry, not equal signs all the way down. So this ends up being just the arctan of root 3 minus the arctan of negative root 3. So if I were to evaluate the arctan, which you could use your calculator to, or you could use your knowledge of the unit circle. So that's where we have a sine value of root 3 over 2 and a cosine value of 1/2. So that would be at 60 degrees, but it would also be so that would be 60 degrees for my or pi in radians, pi over 3 radians. And then for negative root 3, well, there's one value where we have a arctan of or we have a tangent of negative root 3, and that would be at negative 60 degrees. So it would be, that would just be the negative what we had, and you could use your calculator to evaluate these arctans if necessary. And I would then get 1 over root 3, and this just becomes actually plus then, so it'd be times 2 pi over 3, which if I'm then to finish this off, again I want to get my roots out of the basement, I can multiply it by root 3 over root 3, so that would become root 3 times root 3 is 3 times 3 is 9 in the denominator, and I would have 2 root 3 pi in the numerator. Wow. Interesting. Okay, let's keep it rolling so this video doesn't go on for too long. I just got one more example here, and this is another one that's going to involve some trigonometrics here. And so you see the nice thing about that, I think, is why it's like we didn't have to go back and do the resubstitution at the end, because I already had negative 1, or sorry, I already replaced u. So I didn't have to go back and plug in this. So I think that's why actually it would be best for us moving forward to do the u, substitute the bounds in terms of u moving forward. Do you agree? Comment in the video below if you agree. Okay, well, so in this case I have tangent. The only thing about tangent is that tangent doesn't have, it isn't the derivative of anything in our trigonometric chart, right? If we look back here, there is no trigonometric function or function period that has a nice, thank you Ms. Stanford, has a nice clear derivative of tangent. So what we're going to choose to do on this one is break it down as sine of x over x, because after some thought and experimentation, what I realized was that if we write it this way, which is equivalent to tangent, as you all know, if we rewrite it this way, well, what's the integral of cosine? Well, the integral of cosine is negative, oh no, is just straight up sine, right? So, but if I'm to take the derivative of 1 over, like if I end up having to, do this whole function, well, because we have the sine here, when we end up doing u substitution for the cos, it's going to work out quite nicely because the du will account for that sine function. Let me get rid of this sidebar. Sorry if that. So let's see how this, if you can, I think me working it out will be a little bit more clear. So, well, the derivative of that is negative sine dx then. So, what we could then do, well, if these are in terms of x, well, we could see, well, what is, when x is pi over 6, what is u going to be then in this case? Well, what's the cosine of pi over 6? That is 30 degrees, so the cosine would be root 3 over 2. What is, when x is pi over 4, that's 45 degrees, so the cosine is root 2 over, cosine is root 2 over 2. Or some of you may have seen it 1 over root 2, either one is correct. So, I could change my bounds, let me rewrite it, and then rewrite it in terms of u. So what I just need to do is, like, you could just think I need to, instead of having I need to have the negative there, because the du, I could replace negative sine of x dx, forgot that there. If I'm replacing sine dx, but du is negative sine dx, I have to plug in a negative du, which I could just pull out front here. So I would get root 3 over 2 and root 2 over 2. Now that I'm writing it in terms of u, I would then rewrite this as 1 over u du. Because the negative I put over here, and I could now, what I could have maybe done here was, if I solve for specifically what's in there, negative du is replacing the sine and the dx. Put the negative out front, and then I have 1 over u, which now we know is quite nice to integrate. We just get negative, bring that down, natural log of u, absolute value of u, and we are going to evaluate that from root 3 over 2 to root 2 over 2. So when we actually then do the mathematical portion there, check out what's going to happen. Shout out to Michelle who broke down our log rules. Well, it's just going to be the natural log of root 2 over 2 minus the natural log of root 3 over 2. Well, we could actually rewrite this as a quotient according to the quotient rule of logarithms. Negative natural log of root 2 over 2 over root 3 over 2, which is actually just going to give me, did I do these backwards? No. Which is just going to give me, well, do you remember the product rule? I mean the power rule? If we have a coefficient, it could also be written, moved up to be a, so it's like we have a coefficient of -1, a power. So if we want to do the positive logarithm, we could do the positive log and then reciprocate this, because that's all negative power does. And that we don't have to write the divided by 2, because if I were to multiply this over 2 over 2, you can see it's just root 3 over root 2. Well, now, oh my god, I'm probably going to lose some people on that last step. Because now, root 3 over root 2, well, that's the same as, I just rewrote the same thing, but it's the same thing as 3 over 2 to the 1/2 power, right? And then we could put that as a coefficient, because it's vice versa what we did here. So it really just ends up being 1/2 the natural log of 3/2. So it ends up simplifying kind of nicely. But wow, that was some beautiful logarithmic simplification using both the quotient property and the power property. We could actually get it simplified down to 1/2 natural log of 3/2. We could talk about this a bit another time, but these were some really funkalicious examples, these last two, that are requiring us to be creative about finding out what u was, but also use some of the trigonometry and logarithmics that we've learned in the past. Much love, everybody. If you like the video, you could press like. If you dislike it, you could always press dislike. Thank you. Have a good day.